Thanks, Anna. It's a really convoluted title. I'll just be talking about MT, actually, so could have just said that. So I want to start off by acknowledging the traditional owners of the land of which this research has been conducted, so it's the Amiak, Gawler Ranges, and Far West Coast peoples, and I want to pay our respects to the past, present, and future elders. I'm sure you've seen this slide before, so the idea a bit of collecting MT there was, to have a technique perhaps that is actually giving you images up at depth, and then also that sort of plays into some of the processes that might lead to the ore formation. So thinking about the source and the pathways, etc. And that's I guess MT is very good at as a technique to kind of do that. So that was the motivation for collecting the MT. If we step out a little bit, this is not the GP2 era, but this is actually based on older work from the Auslamp that we did a little while ago now. We have a pretty good understanding of what the resistivity distribution is really in the mantle and the crust across the entire state. We have several models for the state, so if I take the one that produced across the Gawler craton and you take a snapshot over it, you get a pretty good idea of what that looks like. So the left-hand side shows you a depth slice of resistivity at 150 kilometers depth from the surface. So where blue colors are really resistive parts, that's usually what we attribute to depleted dry lithosphere that doesn't really have any sign of existing metasomatism, or it's not melted. Any of the red colors here denote areas that where metasomatism is high, or you might have fossil fluid or magma interaction there. And the cross section on the right hand side gives you a bit of an overview of really what the Gawler craton looks like as you step from the west to the east. You'll be familiar with the ICG province here. I hope you can see no, you can't see my cursor. So the ICG province there, just to right off the middle, and then the rest of the Gawler craton is in blue, which means it's fairly depleted, especially sort of. Thank you, Anna. Especially underneath our Gawler craton here, and the area where we are operating right now, the Gawler phase 2 area, is here. So there's some structure there, but as you notice, because the station locations are 50 kilometers apart, the resolution really lacks in the middle to upper crust where you want to have good resolution there. So I'll be talking today about the MT data that we collected across there, so that gives you a bit of an overview of how much better we've done in terms of the station coverage. So if I plot this here across the TMI, all the yellow data points here are actually existing MT data before we did the GP2 survey. So that we had a survey across the seismic reflection line here, along the Eucla there, MT broadband. There's an old GA along the Goma line, and these are the interspersed, the Auslamp stations across it. So if we plot the MT across it, the new one, this is the coverage there. So that gives you a bit of an idea of how much better we're doing. This is not just closing the site spacing, but these are also recording broadband MT instruments and not just long periods. So what that means is you get a much better resolution nearer to the surface as well in terms of the frequency bandwidth that you're dealing with. And it even allows you, Houston talked about the AEM, you could even tie that into the AEM because it has, similar depth penetration. Well, it doesn't have the same depth penetration, but there's overlap between the two techniques. The idea here is to give sort of a background image. So this was 12.5 kilometer spaced grid. That's sort of the backbone. And then there's also two closely spaced profiles that are running across it. And that was put in just because of land access sort of along existing roads or tracks. And then also crossing across areas where we at the time thought there's enhanced nickel content and also gold. So we want to be able to image those. This is just showing some of the data. We're looking at phase sensors. These are really just a depiction of where electrical currents are flowing. So this is for a period of 1 second. So that means every site here looks in the vicinity of just a few kilometers around it. So where currents might be flowing. What you see here is that there's a rough trend that the currents like to flow around some of the gravity highs, which is the background image. So you can see that even the main lithologies that you're imaging in the gravity has some influence of what the MT might show. So that's good to see in the data. And you will see that later in the model as well. In terms of the inversion itself, so we're taking the data that we collect in the field and turning it into a 3D resistivity model of the Earth from basically near the surface and down to depths of into the upper mantle. So that means now 60, 80 kilometers or so, where it's still relatively well constrained. There's some details on the inversion. I'm not really going to go through with it, but it's fairly high resolution where the cell sizes are down to 1.9 kilometers in X and Y direction. So you get relatively good resolution even with that grid. So what I'm going to do now is just kind of step through the different depth slides just to give you a bit of a feel how the area looks like. So we're starting from the upper mantle and we're working our way up to the near surface. So in the mantles on the left-hand side here, you're looking at 60-kilometer depth slice. In all these images, this is where Challenger gold deposit is. Aristarchus, the nickel prospect that we have, is sort of sitting around there. And you can always have that sort of grid down here as a comparison, just to kind of check against the TMI. So the upper mantle is still relatively resistive, so the color scale here is on the right-hand side. I should mention this is not the typical color scale that I always use for the ISCG province, because everything here is actually very resistive, which is sort of what we're expecting from an area that has a lot of nickel potential, just high degree melts. We don't really expect really big conductors to be there. And that's, I guess, what we're still seeing in the mantle, that even though there are some of these whitish colors, but it really means they're still on the order of a few thousand ohmmeters, so that's quite resistive. Interestingly, though, the lower crust at 40 and even 28 kilometers, if I go to the next slide, has some areas that are a little bit more primed, that have a bit more conductivity, which is quite interesting. And I'll talk about that a little bit later, of what that might mean. And if you then go into the middle crust, we're at 15 kilometers, what we're starting to emerge is an area that is really quite resistive, or actually very, very resistive. Hardly seen anything like it before. But there's also this sort of pathway, and you might see that tracing up towards Challenger, which is an interesting finding. So that's actually a bit more conductive. But still it's relative, right? So this is still on the order of 1,000 ohmmeters, but compared to this area, which is on the order of more than 10,000 or 100,000 ohmmeters, which is extremely resistive. So what do you expect the mid-crust to be is just extremely depleted. So it's probably been completely melted, anything stripped out of it that had any resemblance of fluid in it. And that's pervasive even down into the upper crust. So there's a 7-kilometer depth slice here, so we are now in today's upper crust. And that's really quite pervasive, and also coincides quite well with where we have that gravity high, right? So which is sort of your footprint almost of the mafics. So the upper crust is also very resistive. Then the whole response changes, which is quite interesting. So at 3 kilometers depth, basically on top of that resistor, we have a really strong conductor that's sort of roughly where Aristarchus sits. Not really sure. One theory that might be, if you think about nickel deposits and sulfide saturation points, maybe this is where you have reached it, and you just have a lot of sulfides there at depth. That could be an explanation for the conductor. Otherwise, I'm running out of ideas. If anyone has some, happy to know them. If you go even closer to the surface, actually before I do that, I'm just going to give you a bit of a cross-section just to kind of get your head around the three-dimensionality of the whole thing and how that looks like. So I'm showing you cross-sections, one that kind of goes through roughly in this orientation, and then a bit further up that kind of runs roughly here on the northern end of the resistor and near where Challenger sits. So that's how that looks like. So this is one cross-section, and you can see here this really resistive body in the mid to upper crust again. That really stands out, and where you have the gravity anomaly roughly on top of it. This little blip here is that conductor that sits about 3 kilometers depth. And also interesting, the Karabi shear zone that Mark will, in his next talk, will talk about, is what we think is quite fundamental to the entire story here. Comes up as something that's moderately resistive or conductive, whichever way you want to look at it. But that's sort of bounding it to one side. If you step a bit further into the picture on the right-hand side, that's sort of roughly going, again, Challenger sits about there. You see that around the edges of that kind of resistor, you see a more conductive anomaly coming around, and then the entire lower crust is actually primed. And we think what happens here is that because we do have high-grade metamorphism, that whatever you're imaging now in the mid to upper crust probably has been in the lower crust in the past. Those all come up. Where you have melting occurred, kind of happened in the lower crust in the past, it's now sort of more exhumed, you're sitting a bit more closer to the surface. And anything that's sort of in the lower crust has then sort of been emplaced or refertilized underneath it. And so this is one possible explanation of why you might have, pervasive, relatively higher conductance in the lower crust today. So I want to finish off by looking at quite close to the surface. So this is at 1 kilometer and 3 kilometers depth, and if you followed Phil's talk quite closely, you might see the patterns emerge here, and also Yusen's talk. So there's a lot of structure here because we do see a lot of resolution. There's a quite interesting boundary that happens in the Fowler domain here. That also Mark will talk about it, and Anthony Reed has published some work on that. This is sort of isotopically an interesting boundary actually along there. What really comes out here quite well is sort of what we think is, what are the paleochannels. So you also see that in the MT. So if you look at the image that Phil has shown, so this is just the gravity, again in grayscale. So you can see the paleochannels just hitting there. And if I go back and forth between the MT and the paleochannels, you kind of see that the MT matches that really quite well. So even with that quite widely spaced data set. So it'd be interesting to see actually to overlay what Yusen's shown. I'm sure it tells exactly the same story. But you have 3 different data sets that really constrain your polychannels quite well. So I just want to finish off that there's more products here. There's also 2D inversions along the lines. I don't really have much time to talk about them, but just the fact that you can resolve features with finer detail along 2D than in 3D because you can discretize your model finer. You know, you do tend to resolve some of the upper crustal structure a bit better here, and you can really trace them in between the profiles. There's 3 different profiles. There's one that's the Euclid line of existing data, and these ones here, so this one there and this one there is the new sort of profiles that we collected. And there's a pretty good match between those connectivity pathways there and some of the major faults that kind of run through the area. So you can really flip them up. And if you look from the northeast, so you're flipping the whole image around, that just gives you a different view. So just to conclude, I've got really exciting new info MT data that you can actually also view some of the depth slices on CSIRO now. You can literally just kind of step through the models at 12 different depths. That's been available since yesterday. So thanks to George Goufers. The mineral systems show a crustal footprint, but not like in the ICG world. They don't just always going to be conductive, but also the resistive parts tell a story here, and the nickel for the nickel copper. As I said, the upper mantle beneath the Archean terrain is fairly depleted. It's very resistive. It's kind of what we expected. And we're also kind of adding another data set to delineate paleochannels. And as I said, everything is available for CSIRO. So thanks for that.